this is a joint work, as you just explained. Yeah, basically the work was first published at Models 2019. It was awarded with the Best Paper Award in the Practice and Innovation track. Therefore, we got invited to submit an extended version to the Journal on Software and Systems Modeling. And there it finally got accepted in 2021. And now we're here, and I want to just give you some results of our work. Okay, as probably some of you already know, the automotive domain is really complex when we have a look into modern vehicles, depending on, of course, the options which you may buy. We have 200 ECUs, 100 sensors, actuators, many kilometers of wire harness, so for electric power and communication, and a lot of signals. And basically, this is also the big trouble. 25,000 signals or even more. And the reason for that is more or less historically grown EE architectures, where you just put in more functionality, more software. And so therefore the number of signals which are being transmitted over the complete communication network is just increasing and increasing. And of course, the driving forces today are automated driving, connected mobility, electrification, and shared vehicles. On this slide, I want to show you on the upper right an example for a functional architecture of an electronic park assistance system. The black boxes on the upper right are sensors and actuators. The components in between are just some functional components, and the arrows depict communication. So in these situations, signals are being transmitted from one component to the next component. And as I said, we have maybe 25,000 or even more signals. And for making this technically happen, these signals need to be mapped onto technical things like PDUs. PDU stands for Protocol Data Unit, and those PDUs are then packed together into frames. And these are then the frames for a concrete communication protocol, like for instance, the CAN bus, FlexRay, or Ethernet. And this is a really time-consuming process to map all these signals. And this is basically how it works today. This is the left-hand side. So we have this manual mapping of signals to PDUs to frames of messages. And where we want to go is basically a service-oriented approach where it's not necessary to map manually all those messages, but just to specify which communication pattern works for which service. And usually what we can see are two types of communication patterns. One is the publish-subscribe communication pattern, and the second one is the request-response communication pattern. Both patterns are depicted here graphically. So in the first case, we have just a service that publishes some properties or some behavior, and this can be found by a client. And by this, a publish and subscription mechanism can work. And the second thing is the request-response pattern. And both patterns are supported by some technologies, namely the scalable service-oriented middleware over IP. This is SumIP, and the data distribution service, DDS. Both types of communication middleware are supported, for instance, by the AutoSAR Adaptive Platform. And why do we use services? We use services because we have many, many thousands of functions, and those functions are just really complicated. And what we try is to break down the functions into smaller reusable components. And these components are what we call services. So like these colorful blocks here are services. And by putting them together, by playing Lego game, we build up reusable functionalities. And when we have such an service-oriented architecture, of course, this is on the software side, this is enough. This is not enough. We moreover need to have a technical execution platform. And there's currently the trend to go to more centralized architectures, as I depicted here on the left-hand side, where we have in the middle some kind of modular computing platform, which consists of many, many, many different ECUs or cores at the end. And those this powerful centralized computing platform is then maybe connected to so-called zonal integration platforms, which are capable of integrating also legacy components, which maybe are not using Ethernet as communication technology, but maybe LIN or CAN-bus. And this is how future architectures, and also maybe a little bit today in current architectures, maybe if we have a look into what Volkswagen is doing or what Tesla is doing, or we are sometimes already seeing such kind of architecture. On the right-hand side, we have a more detailed view on that, where I also depicted that we have many cores, and depending on the level of safety which you want to satisfy, those cores can be in a master-slave configuration or maybe run in lockstep. And a powerful communication network, for instance, based on Ethernet, like TSN or AVB, can be used for that. And for our experiments, we used this AVB protocol, which is based on Ethernet. And now it comes the interesting question which we asked ourselves in this pre-development project, namely, if we have a newly designed architectural model from a hardware point of view, and if we have a service architecture where we have rough estimates of how much bandwidth, how much computing power, how much memory a service will need, whether it is possible to find out a deployment and to find out an architecture synthesis which can then, in the next step, being transferred to the regular software development process. So we are already here in an early phase, so we are not specifying the concrete, very detailed behavior of our services, but we are in an early phase and just want to get a rough idea whether the architecture which we envision is basically feasible and to support the architects. So the ingredients are first the new centralized multi-core EE architecture, then we have the resource estimates and then service-oriented architecture, and the question again is whether we can derive from that a system specification for an AUTOSAR adaptive platform software design. So we have several steps which we do. First, of course, we need to model both the hardware platform and the service-oriented architecture. Then we perform design space exploration. Finally, we do timing analysis in order to verify whether our decisions, whether our synthesized candidates actually support all the desired requirements. And then we're going to do the transition from a platform-independent model towards a platform-specific model, namely the AUTOSAR adaptive platform, and do this further steps which are not discussed here in this presentation. Okay, let's start with an architectural model from a service perspective on the left-hand side. So in this case study, we do a level 4 automated driving, meaning we do not have an driver as an failover or backup system, but what we have a redundant system as failover system. And in this case, we have this trajectory planning service, which uses the environmental model, for instance. And this environmental model is deployed twice in our example, namely if the first environmental model does not work correctly anymore, then we have this backup service, and during runtime there needs to be a subscription reconfiguration of our system in order to fail over to the redundant component. And on the right-hand side, we have the hardware topology. So we have the centralized computing platform. We have ECUs, which are the legacy ECUs, namely the driving dynamics ECU, telematic, and a gateway. And as you can see, it's a switched Ethernet topology based on the AVB standard. And we used this gradient-based shaping algorithm for that. Now the question is where to deploy those services here on the left-hand side. For that, we need further information, namely the first information is about the resource requirements for our services. And there we have some rough estimates given, and you can have a look into the paper. There are the more details given about the processor utilization, memory consumption, and the safety classification of each service. And moreover, we have the capabilities of our hardware. So we have 25 cores. Some of those are safety cores. Then we have really high frequency cores and GPUs as well. And of course, we have some memory attached to those components here. And now the question is about the design space exploration, where to deploy which service. And we do for that, we're using this Z3 solver by Microsoft Research, which is able to so basically it's a decision procedure or a theory improver, which is able also to compute Pareto optimized results. And by that, we can synthesize, in our case, 3 different candidate solutions, which are all feasible concerning the memory consumption, bandwidth, safety requirements, and so on. And the next step is we need to verify whether these candidates are actually feasible, which means whether they satisfy the timing requirements. And for that, to verify the timing requirements and also the bandwidth capacity and latency requirements, we use the GronSim simulation tool. This is by Incron, and this is able also to simulate the traffic shaping algorithm. We can simulate load at our nodes at the switch, and also it supports the sum IP subscription, resubscription mechanism, which is all simulated within this tool. And the requirements were that every 30 milliseconds or within 30 milliseconds, we need 3 times a fresh environmental model. And if this is not given, then the system performs a reconfiguration. And for this complete reconfiguration, we have time of 130 milliseconds. Yeah, and the results are that all 3 candidate solutions which have been synthesized are actually valid, which means they are all supporting the bandwidth, the end-to-end latency, and the real-time requirements. And what I have not shown here in this presentation, we furthermore do the transition to the platform dependent model by also generating AUTOSAR XML files. These are the service interface specifications, and then we have state machine formalism in order to specify a high-level behavior of our services, and this is then handed over in the follow-up development process to the engineers to then really specify the behavior of each service. And finally, we also perform the testing on the one hand side from the abstract behavior of the state machines, and in the other side from the implementation of the engineers. So we have 2 different sources of specification and the abstract behavior, such that the tests can be executed at the end. And as what I showed you, I hope I could, in this short period of time and with some technical problems right at the beginning, I could motivate the use of service-oriented architectures. I showed you some ideas about a centralized computing platform, and we used an SMT solver in order to solve this multi-criteria optimization problems to find out candidate solutions. And actually, we were able to verify those solutions at the end.